Professor Christina Lioma from the University of Copenhagen, who's going to talk about pitfalls with ablation in neural network architectures. Thank you.
Thank you very much, and thank you for the invitation. So yes, I'm going to talk about some pitfalls of ablation in neural network architectures. So hold on. Neural networks are one of the most widely used types of machine learning today. They have been applied in several domains with success. And one of the open challenges in their use is being able to explain their output. So being able to understand how the input signal is actually transformed, what types of transformations it undergoes, and how they're responsible for specific outputs. And this is important for a broad range of end users, ranging from users of systems that make decisions that affect users. And now with the new artificial intelligence legislation that is being drafted in the EU and across the world, this is actually an obligation of the developers to actually provide an explanation of algorithmic output. It's also of interest to business developers, boards of ethics, but also computer scientists and engineers who actually need to understand the output of neural networks so that they can refine and improve models. And one of the most popular ways of trying to understand the output of neural networks, especially by developers and computer scientists, is ablation. So on a high level, the idea behind ablation is that given some input, some data input that we have, and that is represented as features, then we run these features through the network, we get an output, and then we take turns removing each of these features every time, comparing the output that we get when a feature is removed to the original output we got when we used all features. And the idea is that any change that we observe in the output when we ablate a feature, we reason that that change is due to the change in the input, the fact that that feature is ablated. So this is a way of kind of trying to trace back the attribution of a feature to the output by removing it and repeating the experiment. And the basic idea is that the more discriminative a feature is, the more predictive power it has. When we ablate it, the bigger the change that we will see in the error of the output, regardless of how we measure that error in terms of accuracy or mean square error or precision or whatever. So to look at a concrete example, let's say that we have a task where we want to classify images as into two types. The first one, images depicting white swans, and the second one is images depicting brown bears. I mean, this is a straightforward task most of the times. However, there can be cases where photographs are taken from specific angles under certain light, where swans are not necessarily purely white, but they might be kind of gray, and bears might also look a bit whitish. And also even the shapes of the animals might be hard to distinguish. So it's not an extremely trivial task all the time. And let's say that we have three features for a data set of this type: color, shape, and texture. And we do experiments using all features. And then we take turns ablating each of those features. And we get an accuracy between 0.78 and 0.75. Then the rationale behind ablation is that we observe the drop in accuracy by using ablation, by ablating each of those features. And we reason that the bigger the drop that we witness, then the more predictive the respective feature is. And having done these standard experiments, the standard interpretation of ablation would be that for these datasets, for these experiments, color is the most predictive feature, because when we ablate it, we see the biggest drop in accuracy. We would also conclude that shape and texture are less predictive than color, because there's no drop in accuracy when we ablate them. And for the same reason that shape and texture are equally predictive features. And this is the strength of ablation, that it's common sense to humans. It gives intuitive explanations. And also it's one of those explainability methods that are post hoc and model agnostic. So they only need the input features and then the output, and they can work with any neural network or any other architecture, no matter how complex, no matter whether it's ensemble or however the input data signal is transformed. However, there is an assumption in this interpretation of ablation. There's an underlying assumption here, and I'm going to show in this talk that this assumption is not always satisfied. The assumption that we make when we interpret ablation like this is that the neural network uses all the features that are available to the network. So for example, when we say that we use all features and we get an accuracy of 0.78, we assume that the network actually uses color, shape, and texture in this example. And when we take turns ablating each feature, again, we assume that the network will use the remaining 2 features that are not ablated. And this is an assumption, but it is not always guaranteed to hold. It's not always the case. We may have cases where features that we think the network uses are in fact ignored by the network. And this can happen. And in this talk, I'm going to show that. So we might have cases where in this experiment, for example, we ablate 1 feature at a time. So these features are ignored definitely by the network, and we know that they are ignored. But there might be other features that are also ignored by the network without us being aware of it. And if this happens, then the standard interpretation that we use when ablating is far from the truth. So for example, the conclusion that color is the most predictive feature, we are no longer certain about that. This is no longer guaranteed. The only thing we can say is that color is more predictive than texture, because we might have experiments where we just use only color or only texture. And again, we cannot make any comparison about the remaining 2 features, shape and texture, because we do not know how predictive shape is. If this happens in these experiments, shape is not used at all. And more than that, we do not even know if 0.78 is the best possible accuracy that these 3 features can give us for this data set and given this setup. Because in these experiments, we're only using either only color or only texture, and we're not even aware of it. So the gist of the problem is captured by this sentence here: features that we think are used may in fact be ignored by neural networks. And this is linked to the complexity of the features that we have available. There is a tendency sometimes for neural networks to use only the simplest feature available to them and to remain invariant to more complex features, to ignore complex features. Not because the complex features are not predictive enough. In fact, we have evidence that this can happen even when every complex feature has significantly greater predictive power than the simple features. And this is an extreme case when this happens, but it does happen. This phenomenon was observed in 2020 by Shah et al., and it is labeled simplicity bias. So the idea is that neural networks have a tendency sometimes to show simplicity bias with respect to feature complexity. So this begs the question, how do we establish the complexity of a feature? How can we measure that? And I'm going to explain that using this illustration here. This is an example of artificial data points that have to be classified into 2 classes, the blue class and the red class. And because these are data points produced artificially, they are distributed in these horizontal bars that you see here. So this is a completely synthetic data set. But let's say that we have input data points that are distributed like this, and the task is to do binary classification, split them into red and blue. Then let's assume that a feature exists in this data set that can define a decision boundary that separates those data points using this vertical line. So we can have data points that are linearly separable, and we can have a feature that actually manages to linearly separate the data exactly like this green line. In this case, this decision boundary defined by this feature would have a perfect accuracy, 100% accuracy, so it would do the job very, very well. And let's say that for the same data set, a second feature existed that could also separate the data points perfectly using 4 linear components all arranged in a zigzag. So the decision boundary defined by that second feature would look like this orange line that you see here. In this case, this feature would also have perfect accuracy. It would perfectly separate the points. However, the orange feature is composed of 4 linear pieces, whereas the green feature, the green decision boundary, consists of one only linear piece. And basically the complexity of the feature is approximated by the number of linear pieces in the decision boundary that gives the best possible accuracy when we use only that feature. So in this case, the orange feature is a complex one, and the green decision boundary is defined by a simple feature. Now, one might think, okay, so we have a simple feature that gives perfect accuracy and a complex feature that gives perfect accuracy. So it's good if the neural network uses the simple feature, because the simplest solution that gives the best possible results is always the best. We know that. So why would we want the network to use the complex feature, and what's the problem with not doing that? And basically the problem with that has to do with the margin of the decision boundary. So the margin is defined as the minimum distance between any data point and the decision boundary. So for example, for the green decision boundary that is defined by the simple feature, that margin is very, very small. So the green vertical line almost touches the red and the blue points. Whereas for the complex feature, the decision boundary that is defined for the complex feature has a bigger margin that separates the actual decision boundary from the input points. And we want that margin to be big, because that means that the classifier that we learn, the function that we learn through the network, is more robust and more generalizable. Because the bigger the margin, then the higher the probability that when we have unseen data coming in that is produced by the same distribution, we will have a higher probability that the decision boundary with a larger margin will classify those points correctly. Whereas if the margin is very small, the probability of that happening is smaller. So the generalizability is not as strong as for having a larger margin. So the margin really does matter. And ideally what we want to have is a decision boundary that is defined by features that perfectly, or that has a high accuracy in classification, but also a decision boundary that has a big enough margin so that we can have some higher probability of generalization and robustness. So this is feature complexity, and I'm going to present some experiments now on synthetic data, illustrating the case of simplicity bias. So in the case of the network ignoring complex features. So the first type of synthetic data set is produced by generating data points that belong to two classes that you see here as the blue class and the red class. And 95% of the points are easily linearly separable, but 5% of the data points are generated with noise. So there is an overlap there in the middle where the arrow points, and that makes this classification, this data set a bit trickier to classify. And using this generation of data points, we can have a data set that looks like this. So this is very similar to the data set I showed earlier for defining feature complexity. The only difference is that this data set can no longer be perfectly classified using a linear line, a vertical line, a linear decision boundary of one piece. The only way we can have perfect classification is if we have a decision boundary that zigzags across the different classes. So on this synthetic data set, we have one simple feature, which is one linear piece. And we know that this simple feature has a predictive power of 95% accuracy, because we know that 5% of the points cannot be classified using one linear piece. And then we have multiple complex features of 7 linear pieces that zigzag across the data points. And each of them have 100% predictive powers. So they're generated like that artificially, so we control that. And I believe we use 14 different types of complex features that are defined in terms of 7 linear pieces. These are experiments that they were initially done by Shah et al., and we have fully reproduced them. So we experiment with a fully connected neural network, and we vary the number of nodes from 100 to 300, and also the number of layers from 1 to 2. So this is not a very deep architecture. It's relatively speaking, a small network, broad, but small. So first we experiment using all features, and then we see that we get an accuracy of close to between 0.94 and 0.95 approximately. So this is very close to the best possible performance that the simple feature can give us. But it's not close to the perfect accuracy that we know the 14 complex features that we use can give us. So already this is an indication that the network is not making the most of the discriminative features that are available to it. We then do another experiment where we randomly perturb the complex features. So we actually distort each of the complex features intentionally in a controlled way. And when we repeat the experiments, we witness a very, very small and insignificant change in performance. So distorting the complex features, which are the more discriminative, does not change much the decision of the network. The change ranges between 0.1% and 0.3%. So this is really negligible. And these small percentages are due to the fact that these experiments are averages across several folds. We use X-fold validation. And then we do further experiments where we do the same. So we distort the single simple feature that we have available. And there we see that when we distort the feature, then the simple feature accuracy drops to almost 0.5, 0.49, and so on. So we have a very significant drop in performance when we distort the simple feature, and we have negligible, almost no change in performance when we perturb the complex features. So what this tells us is that the neural network is not making use of the complex features, even though we have 14 of them and only one simple feature. And even though the complex features have much more discriminative power than the simple feature. So the network remains invariant to complex features for this synthetic data set in this case. And similar findings hold as we increase the number of complex features to 249. So really trying to saturate the sample of features that we have with complex expressive features. This doesn't make a difference in this case. Similar findings hold for experiments with different types of neural network architectures, convolutional and sequential neural networks. And also for different variations of synthetic data sets. So on the left here, you see a data set where the data points are linearly separable between the two classes. And again, a simple feature could give perfect accuracy, but it would not have high generalizability. And on the right-hand side, we have a data set where no linear decision boundary consisting only of one linear piece could ever give perfect accuracy. What we need is at least a zigzag decision boundary of 5 slabs that could separate those points. And then we get similar findings in these data sets as well. So in these synthetic data sets, this finding holds that neural networks, the ones we use here, show a bias towards using only the simplest feature available to them and ignoring more complex features. Now, I have shown this on synthetic data, and in fact, even the definition of feature complexity is defined on synthetic data. So I defined it as the number of linear pieces in the decision boundary that can separate the data. And this definition is not as easy to apply to real data because real input data tend to be arranged and distributed in ways that are not as clearly separable. So what we have done is that we have used a piecewise linear classifier in order to get the number of linear pieces in the decision boundaries per feature. So that means that we do experiments where we use one feature at a time. And using one feature at a time, we train a piecewise linear classifier. And then we observe how many linear pieces this classifier converges to. So just if you're not familiar with piecewise linear classifiers, these are classifiers that define a decision boundary that consists of the minimum number of linear pieces that will give the best possible accuracy. So it matches exactly the definition of feature complexity. And you can see here in this graph an example, an illustration of a decision boundary defined by a piecewise linear classifier that consists of m linear pieces And these are parameterized by m-1 breakpoints. So the number of breakpoints basically defines the number of linear pieces. So for any data set, we train each feature separately with this piecewise linear classifier until it converges. And specifically what we train is the number of linear pieces that you see here on the x-axis. This is the breakpoints that define the linear pieces. And as we begin the training, accuracy increases. Accuracy is depicted on the y-axis. And then at some point, accuracy stops increasing. So we have convergence. And this is the minimum number of linear pieces that gives the best possible accuracy. And we use this number of breakpoints or linear pieces as an approximation of feature complexity. And in fact, this approximation is 100% correct on all the synthetic data sets that we have used. So it works. Now, having this definition of feature complexity on real data, we do some experiments also on some real data sets. I'm going to show some findings on a biological data set that consists of classifying chemicals into whether they're biodegradable or not. So we have binary classification, and the features of those chemicals are molecular descriptors. And we have, in the version of the data set we used here, we have 11 features and 1,055 chemicals. Out of those 11 features, 3 are simple features and 8 are complex. So, and this is the balance, the distribution of simple versus complex features. And we have split them into these two classes according to the number of linear pieces that the piecewise linear classifier converges to for each of those features. So using a fully connected neural network, we do experiments using all features, simple and complex, and we get an accuracy of 0.78 approximately. And then we do experiments using only the single most complex feature, and we get an accuracy of 0.89. So what this tells us is that there exists a complex feature in this data set that is very predictive. It has a high predictive power of 0.89. And when this feature is used in combination with all other features in the collection, then the network doesn't make the most of the predictive power of that feature. Then we go on and we do experiments where we, similarly to before, we perturb this single most complex feature. And also in a separate experiment, we simply ablate, we remove the simple most complex feature. And in both of those experiments, we see that the accuracy that we get is identical to the accuracy we get when we use all features. So again, like in the synthetic experiments before, it doesn't matter if we distort the complex feature or we ablate it, accuracy does not change. So the neural network remains invariant to the single most complex feature in this collection, which is also the most predictive feature in this collection. And if the network had made use of that single complex feature, then accuracy would have been 12% higher. So this is a significant loss. But we also can reason that the fact that the network doesn't use the most complex feature results in lower generalizability, because we know that the margin defined by the decision boundary will be smaller than the margin that would have been defined if the complex feature had been used. And what this also says with respect to ablation is that any ablation that we apply to these experiments would give unreliable results, because we cannot be certain that we are actually making the comparisons that we think we are making with ablation when the network fails to use the single most complex feature. Experiments on the remaining complex features in this data set do not give us strong results, but they do give findings in the similar direction. So we see that when we perturb the remaining complex features, overall, we have a very small drop in accuracy between 0.46% and 1.6%. And also the same happens when we ablate each of the complex features in the data set. We have a very negligible drop in accuracy. So largely the network seems to remain largely invariant to any variations in these complex features. So far, the finding, the conclusion that we can draw from these experiments on real and synthetic data sets these datasets is that neural networks may use, there are occasions where they may use only simple features and ignore complex features available to them. This does not happen all the time. We have shown that on a synthetic dataset, different versions of synthetic datasets, and we have shown that on one real-life dataset. But we have also done experiments on other real-life datasets, and we did not witness that. So this is not something that happens always. This is something that may happen sometimes. And when it does happen, then it definitely invalidates ablation, because we cannot rely on the network comparisons that we think we are making with respect to what features are used and what output they produce. So this begs two questions. Naturally, why does this happen? When do neural networks actually ignore complex features and use only simple features? And the second question is, are there alternatives to ablation that we can use to explain, to attribute features to output that are not affected by simplicity bias? Are there more reliable alternatives? I'll take both of these questions. The first question, why does this happen? Why does this simplicity bias occur in neural networks? And the quick answer is that we do not know. When I say we, I do not mean only me and my group. I mean the scientific community does not know yet. There are lines of investigation, and there are two main lines of investigation, potential explanations, but without certainty yet. The first one is that this could be caused by the fact that when we start training neural networks, we might use gradient-based optimization algorithms that might get stuck at local minima. And how this links to simple features is that at the beginning of the training of this optimization, it is the simple features that have a predominant role. So when the algorithm starts learning the gradients, it is the gradient of the simple features, the simplest features that it will start learning. And if that tends to make the model get stuck in a local minimum, then there might be cases where the model is not able to get out of this local minimum to escape. And then we get stuck with predictions that basically use only this most simple feature. I understand I'm being fuzzy about this because this is not conclusive. This is just one indication, and it's being investigated right now. The second possible explanation of simplicity bias is related to the representation of input data points by neural networks. So neural networks, they learn the probability of some classification label given some data input points, and that by defining a decision boundary that separates the input data into classification regions. And you see here an example where we have points classified as green and points classified as red. And what happens is that these real concrete data, these input points are internally represented, they are encoded, and they are lifted in a high dimension that is not necessarily interpretable by humans. So we have like embeddings and so on. We have high dimensional representations of our data. And these encodings in this high dimensional space, they may end up occupying a much larger classification region than the region originally occupied by the actual real input data, the unencoded input data. And we might have cases where some encodings, specific encodings of data points, may be very, very well placed within a classification region, and that will result in very high confidence of the model that they are classified correctly. But they might also be located very far away from the classification region occupied by the original input data points. And it might happen that we end up with a model having very, very high confidence in some representations of input data that maybe they have they are correlated with some very, very simple features, and they are located far away from our input data points. And this can tip the model towards showing a bias towards using exclusively or predominantly simple features at the expense of more complex features. Again, I'm using vague language because this is just one direction that is being investigated right now. Now, the second question was, are there any alternatives to ablation that are resistant to simplicity bias? And the answer here is not vague, it's straightforward. Yes, there is. And one of the best ones is Shapley's value. This is an algorithm that was invented by Shapley in the 50s. He was an economist and he won the Nobel Prize a few years later. And basically how this is used in machine learning is that this value Shapley's value approximates the expected marginal contribution of each feature to the output that is produced. And in order to do that, we need to run experiments with all possible combinations of features that are available to us. So with ablation, what we do is that we run experiments with all features and then experiments where we ablate one feature at a time, we remove one feature at a time. But with Shapley's value, we need to do experiments with all possible combinations of features. And clearly this is intractable. I mean, this would be this would cost a lot in terms of time, memory, and so on. So very often this Shapley's value is approximated by random sampling, and Monte Carlo is one of the best ways of doing that. And these results, basically approximations of Shapley's value with Monte Carlo sampling, are very, very reliable. They give us a value where if it is 0, then that definitely means that the feature that we get a 0 value for does not contribute at all to the output. And using that value, we can detect which features are ignored by the network, even if these features are given to the network. And here's just for illustration purposes, 2 synthetic data sets at the top of the monitor and 2 figures with Shapley values at the bottom half of the monitor. So on the x-axis, we have Shapley's value. At the center, we have 0. That means a feature does not contribute at all to the neural network. And then we have values that are positive or negative. And for the sake of these experiments, you can ignore the sign. It doesn't matter if the contribution is positive or negative. This is just a byproduct of random sampling with Monte Carlo. And on the y-axis, we have in the first line a simple feature that has only one linear piece in its decision boundary. And then we have a series of other more complex features. And what we see is that at the top, for the simplest feature, then we have high Shapley values. That means that the simplest feature actually contributes a lot to the output of the neural network. And for all the remaining complex features, we have values that are very, very close to 0. They are condensed around 0. So we see very little contribution of complex features to the output. And this is something that ablation cannot always capture, but Shapley's value does. So to wrap up, ablation is one of the standard ways of understanding and explaining neural network output, and it's used broadly by computer scientists. However, the problem is that neural networks, on some cases, are subject to simplicity bias. And that means sometimes they may end up ignoring completely complex, predictive, discriminative features and use only simple features. And this is something that ablation cannot capture. And basically that means that applying ablation on top of these experiments invalidates any conclusions that we draw from that. And also simplicity bias in itself, it can hurt accuracy overall, but also generalizability and robustness of the function that the network learns. And we have shown that on experiments on synthetic and real data, but I want to emphasize that it doesn't happen always. It happens on some data, and we unfortunately do not know yet what are the conditions precisely that causes and how we can avoid having that. So some recommendations for moving ahead. The first one is simply to replace ablation by Shapley's value. There exist packages in Python, readily available libraries that can do that. It's a much better practice, much more robust to simplicity bias. And the next recommendation is to invest effort in more robust learning and training. For example, paying attention to avoid situations where the network gets stuck in local minima, or paying attention to how our input data is represented, how encodings are produced, and so on. And with that, I will conclude. Thank you very much, and I'm open for questions.
Thank you so much.